I will be discussing the fluid mechanics of ice hockey for my fluids final presentation. So, how does ice skating work? There is one generally accepted explanation of how ice skating works, where of the skater's pressure is focused on two small blades. This is a design of hockey skates. I will say that figure skates and speed skates are built and operate a little bit differently, but my presentation is going to focus mostly on hockey skates. So the pressure on the small point of two blades causes a thin layer of ice to melt into water, and this water acts as a lubrication layer, and the skater glides on this water, which then refreezes quickly due to the low temperature of the ice below. So, like I said, this is the generally accepted viewpoint of how ice skating works. However, there are more factors that may come into play other than just a full contact water film, and that's what I'll be talking about in this presentation. So, the main two elements of this initial explanation are pressure melting and friction melting. The melted water layer consists of a sheared laminar couette flow, and it must have zero velocity along the ice-water boundary, which means that the water is not moving in accordance to the ice. And it also has a velocity equal to the skater's speed along the water skate boundary. So this means that while the water is still where in contact with the ice, the surface water that is in contact with the skate blade is flowing at a speed equivalent to the speed of the person skating on it. So this water layer is generated by shear stress force, and it is reduced in thickness by squeeze flow, which allows for the refreezing of the water. So this first picture here is a diagram of the skate blade and water on the ice. And the second photo is a diagram of couette flow, which is the flow of a viscous fluid in the space between two surfaces, one of which is moving tangentially relative to the other. So in this case, we have the stationary boundary plate being the ice, and then the fluid is our liquid, our water, moving with the velocity of the skater's blade. Our next possible elements involved are quasi-liquid layers and flash heating. We have a quasi-liquid layer between the ice and skates that reduces surface energy at the boundary, which allows for slipperiness along with frictional heating. And then we have flash heating, which is produced in isolated asperities and could cause softening in individual spots rather than bulk melting. So if we look at this diagram with these three possibilities, which is basically including uneven blades and uneven ice and a combination of the two, we have spots where the blade or ice are scraping against each other more could potentially be sources of flash heating since there's more friction at those points. So wherever those peaks are intersecting with each other would cause more friction and therefore create this flash heating that could cause individual points of heat. So some experiments were performed to test these hypotheses. I was unfortunately not able to test these myself because the rink closed 4 days before it was supposed to, which was very unfortunate and sad for me. But I was able to get some good data from these older experiments. One of these experiments tested a single foot skate gliding through an infrared and high-speed camera at around 2 to 4 meters per second. And they measured the ice surface temperature after the skate goes by, the rut width, the rut depth, and the rut temperature. The rut being that carving of the ice behind the skate blade. So after performing the experiment, the authors found that the ruts were not smoothly warmed and that there were isolated warmer locations in the rut. So if you look at that infrared image on the right, you can see warmer regions. And so this would imply the existence of the flash heating we talked about earlier as one of the potential sources of heating and melting. So those little red points in the rut would be the points of, an uneven skate blade or something like that that causes flash heating, and those are what you see in that diagram. So, but also they discussed that rather than just uneven blades and uneven ice, irregular skate contact due to crushed particles and slurries broken off from brittle ice by the blade during skating could also create more friction and uneven heating. So ultimately, the paper did not confirm the presence of full contact water films as would have been expected, because that was kind of our initial thought, is that, we're gliding on this full contact water film, but rather It was more consistent with the idea that some uneven flash heating is playing a bit of a part into how ice melts and creates the ideal environment for skating. Another element in ice skating that has been studied is hard versus soft ice. So the temperature of the ice does make a large difference in how well it can be skated on, as well as the fluid dynamics present in the experiment. So the optimal temperature based on the data was found to be around negative 5.5 degrees Celsius for figure skating and negative 9 degrees Celsius for hockey skating. And so the reason for this is because for figure skating, having slightly warmer ice means that figure skaters have an easier time using their toe picks to grip and push off the ice to get more powerful jumps. Whereas on the other hand, hockey skaters who value speed more, this means that having a slightly colder rink is better, as less carving, less grip means you get higher speeds. So that slightly lower temperature is better for hockey. The data also showed that temperatures around or below negative 30 degrees Celsius are not good for skating, because even with high pressure and friction, the ice does not melt as easily enough to create a good gliding surface. And so I wanted to share a personal anecdote about this. On the right is a picture of me on an outdoor rink in the Arctic Circle in Finland. And so at this time of year, the night and morning temperatures were getting to minus 30 Celsius and below, meaning that the ice was likely around this temperature when I skated on it. And this was really interesting because when I skated there, I had a really hard time gripping the ice. It felt like my skates were not sharp at all, despite the fact that they were freshly sharpened. And I could feel how small those ruts were compared to rinks at home. So it was like very obvious from my own personal experience that, I was not gripping the ice very well. So it was really interesting to see that my own experience does line up with the data that shows that very cold ice is in fact bad for skating. Yeah. And then, of course, a shout out to my hockey team, the Benchwarmers, there on the bottom left. Yeah, so thanks for listening to my project. I hope you found it as interesting as I did. And then, of course, here's my references. Thank you.